Welcome back. Like I said, we're going to be solving more optimization problems. Um, so, so basically, the goal is to use calculus to solve verbal problems involving extrema of functions. So here's the example one, and within this example one, we'll do two separate problems. The first one is we want to find two numbers with a sum 13 and maximum product. So we want to find two numbers that sums to 13 but gives us maximum possible product. So if the numbers are x and y, then we want to maximize their product x times y with the constraint that their sum must be 13. So we are trying to find two numbers x and y such that x plus y is 13 and x times y is as big as possible. Well, the function that we want to maximize here is this product, but we wanna be able to express this as a function of one variable only. So we can use the constraint to do that. So rewrite the constraint as y equal to 13 minus x, and then we can plug that in our function that we are trying to optimize. So then the goal becomes to maximize x times y, which is equal to x times 13 minus x, and which is equal to 13x minus x squared. So then we want to find the maximum of this function here. So here's the function that we want to maximize, and we know the drill by now, which is we have to find the derivative of that, which is 13 minus 2x, and so the critical point would be 6.5 because that's the solution to the equation f prime of x is equal to 0. So if f prime of x is equal to 0, that would mean that 13 minus 2x is 0. And if 13 minus 2x is 0, then x has to be 13 over 2, which is 6.5. Okay, so we found exactly one critical point. So let's see if we have a local max or a local mean there. That is, what's the concavity at this critical point? So the second derivative of f would be clearly negative 2. So when we evaluate the second derivative at 6.5, we still get negative 2. So that means at the critical point 6.5, at the only critical point 6.5, the function is concave down, and as a result, it has a local max at this point. But being the only critical point, we have the absolute max there. So f achieves its maximum when x is 6.5. And when x is 6.5, y, recall that y is 13 minus x. So if we go back, y is 13 minus x because x and y sums to 13. So if x is 6.5, then y would be 13 minus that, which is also 6.5. So the answer is the two numbers are 6.5 and 6.5. And notice that there are many numbers that satisfy this constraint, right? For example, 13 and 1, 12 and 1. So if I pick x to be 1 and y to be 12, then x plus y is 13 and x times y would be 12, right? So the product would be 12. Now if I pick x to be 2 and y to be 11, then we still get 13 here, and then 2 times 11, that's going to be 22. So x times y would be 22 in that case. And so there are many ways we can pick the values of x and y, and when we pick x and y to be both equal to 6.5, that's when we get the maximum product. So this is above 36. The product here would be above 36. So the maximum product here would be 6.5 times 6.5, and 6.5 times 6.5, that's 42.25. So the maximum product we can get here is 42.25. Okay, let's look at another example. Here we want to find two positive numbers x and y whose product is 12, and that minimize the expression g, which is equal to 3x plus y. So again, we want to find two positive numbers x and y with product 12 that minimize the expression 3x plus y. So what function are we trying to optimize here? Well, the function we are optimizing is this, and the condition here is that x and x times y is 12. So the constraint here is the x times y is 12, and we can use that to solve for y, and that's going to give us 12 over x, which we can plug in the function to be optimized. And so let's plug that in the function g. So we get g of x would be 3x plus 12x to the negative 1. Now let's figure out the domain of this function here. Well, x and y are positive numbers, so x is clearly positive, and the question now is, can x be any positive number? Well, can I pick x big and still have that x times y is 12? Well, the answer is yes, because you know whatever x we pick, so maybe we can pick x to be if we pick x to be 100, then y would be 0.12, and still the product of x and y would be 12. I can pick x to be 1,000 and then y to be 0.012, and still the product of x and y would be 12. So x could be any positive number. So the domain for this function would be all positive real numbers. All right, so to find the minimum value of this function, then on this domain, we find the derivative, which is 3 minus 12x to the negative 2, and if we simplify that, we're going to get 3x squared minus 12 divided by x squared. And we see that this derivative is undefined when x is 0, but that's not in the domain, so we don't care about 0. And the derivative is 0 when 3x squared minus 12 is 0. So if we factor out the numerator, we get 3 times x plus 2 times x minus 2, and we see that the derivative would be 0 when x is either 2 or negative 2. So those are the critical points. We got 2 of them. So notice that even though we got 2 of them, negative 2 is not in the domain. So we discard the negative 2. So then we have only one critical point between 0 and infinity, and that's 2. So now let's figure out whether the function is concave up or down at 2. By using the second derivative test, this is the first derivative of g. So the second derivative would be 24x to the negative 3. So the second derivative evaluated at 2 would be 24 over 2 cubed, which is positive. So that means the function is concave up at 2. So it has the local minimum at 2. But since this is the only critical number we have on the domain, then this has to be the absolute minimum. So g achieves its minimum when x is 2. Well, when x is 2, then what is y? Y is 12 over x, which means 12 over 2, which is 6. So notice that if 6 and 2 their product is 12, and that's what, if we pick x and y in this way, then they maximize the expression for g, which is this. So notice that, the other part, we could pick x and y to be 3 and 4. So their product would be, product of 3 and 4 would be 12, and then when we plug in 3 and 4 here, we get 9 plus 4, which is 13. So that we would be getting 13 if we pick x and y to be 3 and 4. If we pick x and y to be 2 and 6, then we're going to get 6 and 6 here, so that's 12. We're going to get 12 for the value of g if we pick x to be 2, y to be 6. So you can see that there are many different ways we can pick values of x and y so that their product is 12. But we want to pick the one that gives us the minimum value of g, and the minimum value of g occurs when we pick x to be 2 and y to be 6. Okay, so I'm going to stop here, and in the next video we will be solving this example too.